When the pH is 7, then it's a case where the sample is neither acid nor base. But less than 7, it's an acid, we say. More than 7, it's a base all the way.
In 1923, so this is about 40 years after Arrhenius' theory, so 40 years afterwards. In 1923, we had two people, Bronsted and Lowry, which were independent. So one was Swedish, I think, and the other one was British. And they both came up with the same idea, a new theory of acids and bases. And this theory had all to do with proton acceptors, which were the actual bases, and proton donors, which were the actual acids. And we're going to go over this in a second. The reason why often, Arrhenius, for example, 4 years earlier, was convinced that hydrogen concentration caused something to be an acid. And it makes sense when it comes to proton donators and acceptors, because if you're looking at hydrogen, what it has one, in a normal hydrogen element, has one proton and one electron. Now when it comes to an actual ion, what happens is we go from H to H+, and what that means is it has one more proton than it has electrons. So it has no electrons, it only has a proton. So a hydrogen ion itself is an actual proton. It only has one proton and has no electrons, therefore it's more or less a proton. Which is why, well, you'll see in a second, why hydrogen ions themselves fit in that concept of proton donors when it comes to being acids. So you need to remember these names, and especially their last name, Johannes Bronsted and Thomas Lowry, and what they came up with. So they came up with the theory of acids are your proton donors, and your bases are your proton acceptors. So that was their idea, and we will go over that now. So in this case, if we have an acid, so for example, this could be hydrochloric acid. It has the acid and it has this hydrogen attached as well. And we have a base which has no hydrogen attached, or hasn't grabbed that hydrogen yet. So we're saying that the acid itself is the donor. In a second it will donate that hydrogen, and the base here will be the acceptor. In a second it will accept the hydrogen. And you can see that when it comes to the reactants. So these here are our reactants. And as you can see, this one has now donated, so it has lost the hydrogen, this acid, A for acid, and then B has accepted the hydrogen, so it has accepted the hydrogen. So thereby, what makes something an acid? Well, it makes something an acid if it donates a proton, which in this case is our hydrogen, right? Remember I said that H+ is more or less just a proton. So in this case, our hydrogen has donated a proton, and our base has accepted a proton. Thereby, this is an acid, and this is a base. That was the idea behind it. And we'll go over just quick examples, to show you how that goes when it comes to an actual acid and base. So in this case, we have hydrochloric acid, which we obviously know it's going to be acting as an acid. In this case, water, which we don't often consider a base, will actually be the base itself, because what you'll see in a second is the actual water will accept the hydrogen, so thereby the water is the base itself. So here what we can see is in our reactants we have a chloride ion, which is the same as our hydrochloric acid, just with no hydrogen. So it's donated the hydrogen, thereby it donates a proton. And in the case of water, it is accepted. So this is the water in the reactants, and this is the water in the products. And as you can see, the water itself has accepted a proton. So in this case, the water is our base, and the acid is our acid. The hydrochloric acid is our acid. So it's not to do with hydrogens or oxides, which was what Arrhenius was talking about. Arrhenius was talking about hydrogen oxides. It's more important which one accepts a proton and which one donates a proton. That's what determines acids and bases, not what if they have hydrogen ions that they give off or hydroxyl ions. There are some examples where they don't give hydrogen ions, but they're still an acid because they donated a proton. Now another example would be water. So in this case, we've got water and water. They're reacting. And what you can see here, so this one, what happens to this one, is it had H2O, and now it has OH minus. So here it's actually donated a hydrogen, has one less hydrogen. So this one is the donor. And this one, in this case, this hydrogen, this water molecule, has actually accepted hydrogen. So it is the acceptor. And remember, according to the definition, the acceptor will be the base. So this will be the base. And the donor will be the acid. So in this case, the acid. So water can act as both an acid and a base. So what you should remember when it comes to finding out which one is the Bronsted-Lowry acid, which one is the base, you should actually look at the reaction. And you need to look at what's actually happening. Which one is accepting a proton and which one is giving away a proton. And that's how you determine which one's the acid and which one's the base. But I hope that was useful.
Thank you for watching.